Hi again, welcome back to this little mini course I'm doing where I'm trying to teach high schoolers how to do quantum mechanics, which is the basic math behind it. This chapter is going to be observables, expectation values, and operators. So what does all that mean? So I promised you in the last video that wave functions should be used to find whatever you wanted about the system. It's this Swiss Army knife where you can poke and prod at it and manipulate it and do all these things to it to get out different information about the system. And through that, you can use the wave function to find whatever you want. And so one of the main ways you're going to do that is through operators. So you're going to find the expectation values of observables by applying operators. Now, what does that mean? So an observable is just a property of a quantum system that can be measured. So if you think back to like classical physics, classical mechanics, that could be position, momentum, kinetic energy, speed or velocity, or whatever you want. Any actual observable property. So we're not even getting into the whole quantum mysticism here. This is just like a typical property that you're gonna observe. Now, expectation values of an observable is where the quantum part comes in. So as you know about quantum particles, they don't have a definite position. They don't have a definite momentum, if you remember Heisenberg's uncertainty principle. So these observables are never going to have one definite value. If you have a ball, that ball is going to be going at a definite velocity. It's going to have a definite location. Quantum particles don't have that. They exist, and they have these probability distributions of all these different observables, not just position, as you would have seen from that wave function where you have the probability distribution. It's also every other observable tied to all that stuff. So if you were to try to find, you could think of it as the average of one of those observables, the average value, then that would be the expectation value. Now, it's technically not the average value because once you observe the particle, then the wave function collapses. It's no longer in that wave function. But if you were to, let's say, set up an experiment where you have an electron in a certain wave with a certain wave function, and you set up that experiment 100 different times. So 100 different times you set up an electron in essentially the same wave function over and over and over again. The average value of those experiments for the position of that electron, for example, would be the expectation value for the position of that electron. So you can think of it as your average position. So if you have the expectation value of the position, that's your average position. Expectation value of the momentum, that's your average momentum, etc., etc., etc. And then operators are mathematical objects that you apply to functions. So if you think about a function as a mathematical object that takes in values, takes in numbers, and outputs a new number, a new value, an operator is kind of like a function of a function. So you take in a function and you get a new function out of it. So it just does things to function. That could be multiplying it by 4, or it could be like a derivative times a bunch of constants times another derivative with respect to a different. It gets pretty sophisticated, but for now that's all you have to do. It takes a function, outputs a new function. And expectation values are noted by these brackets right here. So for example, the expectation value of x is going to be like this, where you have x in these little brackets right here, and that's just going to mean this is the average location of the particle, even though technically not the average, but you can think of it as the average location of the particle. And the hat is what denotes an operator. So if you have, for example, a hat, that is the operator a acting on, let's say, f of x. So that would be how you write the operator a acting on f of x. So if we wanted to find the expectation value of, let's say, the position for some wave function, some particle in some quantum state described by the wave function, we're going to need to find essentially its average position. So let's take another look at averages, a little more in-depth look, and try to see them in a different light. So I'm going to build this kind of argument for you. So let's say you have an experiment and you do 10 trials of this experiment, and every trial could result in one of 5 outcomes. And the outcomes are signified by O here, so O1 through 5. And each of these 5 outcomes has some numerical value. So like O1 could be like 3, and O5 could be like 0.6, I don't know, something like that. And let's say you do these 10 trials and you get 1 occurrence of O1, 3 occurrences of O2, all the way down here. So if I were to tell you what's the average value, then what's the average value you're going to get from running a trial, right? You're going to add up the amount of times O1 happened times O1, plus the amount of times O2 happened times O2, plus the amount of times O3 happened times O3, all the way down to O5. And then you're going to put that all over the number of trials that you had, right? That's your typical average formula. And if you think about how you can split up multiple terms in a numerator over the same denominator into multiple different fractions, you can get out this, right? So you have 1/10 O1 plus 3/10 O2 plus 4/10 O3 plus 1/10 O4 plus 1/10 O5, right? So another way you could look at these little fractions here, the 1/10, the 3/10, the 4/10, are as the probability of this, of O whatever, ON happening. So the 10th here is the probability, and the O here is the value. So what you're doing in reality when you have this formula is you're summing up the probability times the value, right? You have you're multiplying the probability by the value for every single value that you're going to have, that you could possibly have. And that includes ones where you maybe don't have any happen at all, so the probability is going to be 0. And you add all those up, and that's how you get the average, right? So that's if you have a discrete number of outcomes that could happen. So in the experiment I showed you before, there's 5 possible outcomes. There's nothing other than that, right? If you were to try to apply that to a continuous environment, like position, for example. Position, there's an infinite number of points between 0 and 1 on the number line, right? If you have 0 and 1, you could have, 0.5. You could also have 0.5 and then 50 zeros and 1, right? This is a continuous number line. You're not going to have, it doesn't have to be 0 or 1 or even like tenths, it could be anything in between there. It's a completely continuous thing. And when you're doing a summation on with continuous values instead of discrete values, what you're typically going to do is have an integral. So that's exactly what you do here. So if you wanted to find the average value of something that's continuous and has continuous x values, or continuous, I guess in this case, v values, then you're going to do the integral. You're going to basically sum up all the tiny little slivers of probability times value. So if we were to apply that to quantum mechanics, what we've learned so far, well, we have a probability function for position, which is the magnitude squared of the wave function, right? So the magnitude squared of the wave function, that's going to give you the probability of the particle being in whatever position. So from that, you can find that the expectation value of x is going to be given by x, the value, x, the value, times the probability distribution, which is the probability. And that is going to be summed up over all space, because there's all the different possible values of x with respect to x. And so I'm going to do something that's going to not make sense right now, but it'll make sense in a few seconds. So if you use the commutative property, that's the expectation value of x. If you use the commutative property of multiplication, what you can do is you can split the magnitude squared up into the wave function multiplied by its complex conjugate, and you could throw the x in between them. And what I've just done there is put this into operator form. So we just made our first operator, the operator x hat. So I'm going to show you the two base operators that you're just going to have to kind of trust me on, and you can derive the second one later if you want. I just kind of showed you what the first one is, but we can use these to get all the other operators. So we have here x hat equals x, right? So we just got that. We also have p hat equals negative I h bar times the partial derivative with respect to x. Now that seems pretty out there, but I'll break it down for you. So if we go back to this x hat equals x, right? This is going to be the position operator. So the expectation value of x is going to be equal to the complex conjugate of psi times x hat acting on psi of xt over dx, and that's going to be overall space, right? Similarly, with the momentum operator, this is going to show momentum, and similarly, if you want to get the expectation value of the momentum of a particle, or of a particle, then you're going to take the integral over all real space of psi star times negative I h bar times the partial derivative of psi with respect to x dx. So, okay, what does all that mean? So, first of all, h bar is called the reduced Planck's constant. This is a constant value. It's given by h over 2 pi, and h is Planck's constant. And you can look up the value of that if you want. And it's just going to be a constant value, and you're going to find it everywhere throughout quantum mechanics. So just get used to seeing that. Again, I, as you know, is the imaginary number, and this partial derivative, now what does that mean? So, psi is not just in terms of one parameter, it's in terms of x and t. So if you ever want to take the derivative of psi with respect to any value, you have to recognize that this is in terms of two values, not in terms of one. There's two parameters. So this is something you're going to learn in, I think, your freshman year of college. You have these partial derivatives. So if I wanted to take, for example, the partial derivative of psi with respect to x, what that's going to be is essentially, if you hold t constant, what's the derivative of psi with respect to x? So if you pretend that t can't change at all, if you freeze the psi in time, that's what the partial derivative of x is. You freeze psi in time and then take the derivative with respect to x. So the derivation for the momentum operator can only really come after we find the Schrodinger equation, and that's in the next video. So next video you'll have the tools to derive this, though I mean honestly it's just going to be easier to kind of take my word for it. This is the momentum operator. Now these are only two operators, so why am I calling them the two main operators? Well, there's a reason for that too. So you can use these two operators with your classical mechanics knowledge to basically get whatever other observable you want. So let's take, for example, kinetic energy, which is, again, going to be important later. Kinetic energy, right, as you know from your classical physics courses, is 1/2 mv squared, right? And if you wanted to change that to momentum, momentum is just more frequently used in quantum mechanics. That's going to be p squared over 2m, right? Following? Okay, so if you wanted to then find the kinetic energy operator, k hat, that's going to be the the momentum operator squared over 2m. Now, when I say squared, I don't mean multiplied by itself. I mean applied twice. So what does that mean? So if you have right here, you have negative I h bar times the partial derivative with respect to x squared. What that means is you're going to apply this one big operator twice. So in the case of these two constants right here, those are going to get squared. So if you have, so it's going to be negative I h bar, right, times the partial derivative with respect to x. Sorry, x. That's going to be x. That looks bad. Sorry. Just that's x. Acting on negative I h bar times the partial derivative with respect to x, right? And that's all going to be acting on whatever the function is, and it's always going to be psi, but acting on psi, let's say, right? And so constants exist, or constant coefficients exist independent of differentiation, right? So you can pull these out, like if you were to take the derivative of 2x, right? That's going to be the same thing as if you take the derivative of 2, if you do 2 times the derivative of x, right? So the constant coefficient is completely independent of differentiation. So if you pull the negative I and the h bar out, well, there's a negative 1, the I is an implicit negative 1, or the negative right here is an implicit negative 1, so these two are going to cancel because negative 1 times negative 1 is 1. The i's, right, are going to multiply together to form negative 1, so this I is going to cancel, this I is going to become negative 1. And the h bars are going to multiply by each other this is going to cancel out, and this is going to make h bar squared. That does not look good at all. Sorry, I'm drawing with a mouse here. H bar squared. So it's going to be negative h bar squared, right? And then you're taking, essentially now that all these constants are gone, you're taking the partial derivative with respect to x of the partial derivative with respect to x. Now what's that? That's the second partial derivative with respect to x, which you see right here. So what you get is negative h bar squared times the second partial derivative with respect to x, right? And then the 2m is a constant that was here originally, and that's just going to carry over. So the kinetic energy operator is given by negative h bar squared over 2m times the second partial derivative with respect to x. And if that's applied to psi, then it's the second partial derivative of psi with respect to x. Just from that example, there's a general formula for this. If you have an observable q, and it's a function of x and or p, or position and or momentum, then the expectation value of q is going to be equal to the integral over all real space of the complex conjugate of psi star, times that same operator as a function of, instead of x and p, x and negative I h bar partial derivative with respect to x, and that's applied to psi. And that's going to give you the average value or the expectation value of whatever this observable is. So now you can use the wave function. I hope that made a little bit of sense. Now you can use the wave function to find whatever observable you want. So that's all I got for this one.